today, essentially, the goal is to have a small excursion into the wild of the web with a focus on regular expressions. Okay, so that's the summary of this lecture. To get deeper into the web, we'll need to use some interesting techniques here. And this will be the technique of string solvers. Okay, we'll apply it to some interesting problems on the web. So that's the plan for today. The talk is based on a paper that recently got accepted at CCS, one of the security conferences later this year. And it's in collaboration with people both at Chalmers and Uppsala University, and recently University of Regensburg as part of the group moved there. Okay, so yeah, it's a journey of web application scanning and what we find there. Okay, so web security is a very challenging problem. We rely on the web a lot in different scenarios. And what essentially is problematic on the web, things break at component boundaries, and we use so many different components. So there's a lot of complexity in how the web operates, which makes it very hard to judge the security of the web. There's a lot of work going in this area. So anything from provable security and protocols for the web, proved by construction of secure software. So there's a full range of things going on, and somewhere in this space there's also detection of security vulnerabilities, which is typically done by scanners and crawlers. Okay, so I mentioned some of them here. So essentially, to assess your security or of a particular mechanism, you would typically use a scanner. So this is something what red teams would also use. So it's an essential component of detecting vulnerabilities on the web. Okay, so black box security scanners play a particularly big role here because those can scan for vulnerabilities even without having access to source code. So they're quite popular. So I mentioned here a couple, Arachne and Zap. This would be state-of-the-art scanners that scan for vulnerabilities. So they try to scan the web, crawl around, and look for problems. Okay, so that's the idea. However, the web is complex. There's JavaScript running in the browser, so it's very hard for a scanner to go deeper in the web. So therefore, it's a very active research space where researchers have come with new ways of crawling deeper into web applications, trying to emulate user clicks, events, and trying to kind of reverse engineer navigation graphs of the web pages. So here I mentioned a few research scanners that are pushing on that. And my group is behind one of the scanners called Black Widow, which combines the benefits of the other research scanners and also has its own contributions. So essentially, you try to imitate as much as possible the user behavior on the web. And our navigation graph is not just URLs, it's also user actions on the web. So we try to model the navigation web and even try to inject pieces of data in a web application and see where it shows up, and that way track flows and discover injections. Okay, so that's the state of the art. Okay, so far so good. Now, what's the problem? Well, all of the scanners are really awesome, but as soon as they encounter input validation on the web page, they're often in trouble. Okay, so what do I mean by that? So many web pages, actually you don't see much of them before you register, for example, right? Or before you provide some input. So here we need to provide a phone number or email to proceed. In other cases, you kind of expect number in a certain format. Yet other cases, it'll be only email. Okay, and then you need to kind of match that as a scanner. Okay, it's hard to do that. Other cases, you might have restrictions, like in this case, you need to have username, which is between 6 and 8 characters long. Okay, so only then you can do something meaningful with a web application. So otherwise you're stuck. Or here you can have you need to provide first and last name. Okay, yet another constraint that we need to pass. So yeah, I mean, essentially all the scanning becomes completely irrelevant if you cannot even pass this basic validation checks. So how does this work? How does this form typically work? So essentially, in HTML5, we have a way to request exactly the format we want for the application. And this is done by the pattern feature. Okay, so you write your HTML tag, which asks for some input. And yeah, you see that here we can give explicitly the pattern of the input that we are asking the browser to enforce. Okay, so this might look a bit cryptic if you haven't seen regular expressions, but don't worry, this lecture will will include a tutorial on those, so you'll know exactly what this is about. So yeah, in this case, we are asking for an email, and we provide a particular pattern that email should match, and the browser will enforce that. Okay, the browser will check if what you provide is actually following that pattern. Okay, so in this case, yeah, a bit of notation used in this standard is that yeah, essentially dot means anything, star means multiple times, 0 more times, followed by the @ character, and then anything 0 more times, then the dot, which is escape with a backslash, and then the final part of the string is 2 or 3 lowercase letters, right, from A to Z, 2 or 3. Right? So that's the meaning of this pattern here. Okay, so that's the idea with patterns. And in this talk, I'll use the graphical notation, which may be sometimes easier to follow than the expressions themselves. So yeah, you see any character followed by @ any character dot, and then 2 or 3 letters A to Z. Okay, so yeah, that way will be helpful. Then if I use this pattern and actually run the application, suppose I provide the input me.chalmers.se, okay, they'll be rejected because the @ symbol is missing. Okay. However, if I provide me@chalmers.se, then the string will match, and I'll allow that in the browser. Okay, just to give a taste of a problem here, well, there are other strings the browser will also allow, potentially malicious. Okay, so if I include a script tag, which is often used in cross-site scripting attacks, in fact, my regular expression here doesn't prevent that. Okay, so that's going to be interesting for the rest of the talk. Okay, but yeah, for now, so we have this input validation. Yeah, and typically regular expressions are used as patterns in the input fields. Yeah, so as a kind of introduction to regular expressions. So I mean, regular expressions are used a lot in programming languages for various matching and searching features. But yeah, in the use case that we are interested in today is input validation, right? So this user data and having some requirements on that. Okay. If you think of regular expressions, maybe the first thing that comes to mind is so-called textbook regular expressions. These are the expressions you learn about in a automata course, and they are essentially, yeah, you have a small number of primitives. This is typically how it looks like. You might have a literal character, you might concatenate things, you might alternate, and then you might have iteration. Okay, these are like very basic primitives, and then yeah, in a kind of in those courses on formal grammars, you learn how to transform from regular expression to automaton, some beautiful theory behind this. Okay, all works very nicely. However, if you push more for how regular expressions are used on the web, it's much more complex. Okay, so it's far from textbook expressions. So the ECMA standard for regular expressions that is used in JavaScript in the browsers includes much more than the primitives I showed, and includes, yeah, groups, back references, anchors, lookarounds. So yeah, so we'll see, how this complexity really pops up. For example, this is a typical regular expression used for password verification. So, user tries to come up with a password. The browser says, no, this is too weak. Okay, what would the browser use? Well, based on this pattern, essentially, yeah, we kind of look for, yeah, so this pattern, we use 2 interesting primitives, look aheads, okay, so positive and negative look aheads. And essentially, yeah, what's happening here is that we say that the password must contain at least 1 digit That's the first condition that you see enforced. So give me a point here. So this means that, yeah, positive look ahead. So without consuming string, we're applying a condition saying that, okay, anything followed by digit, so \d is a digit. And then the next positive look ahead says that should be at least one lowercase letter in the same fashion. Then it should be at least one uppercase letter. And this is followed by negative look ahead saying that there should not be any space in the password, which is also a reasonable thing to require. Okay, so all these conditions being piled up, and then finally comes the actual string. And here, there is no more restriction. So anything that satisfies those conditions is accepted. Okay, but yeah, this is already beyond what textbook expressions offer. And for a scanner, okay, this is a challenge. If I encounter a field that has this input validation, okay, how do I pass this, right? How do I come up with an input that satisfies this expression? So that's exactly the goal of this work, to identify input validation, like this regular expression example, and see, how can we pass those checks based on those expressions. And we need to deal with practical regular expressions on the web. Okay, so yeah, if you're versed into web security, you might ask, hey, this is client side, but anything about the coverage of web application is on server side. So in principle, when I'm scanning the web, I can throw away all restrictions that the browser might enforce and supply whatever I want, right? Because the browser check is irrelevant. The only thing that matters what you actually check on server side. Is my password accepted or not on the server? Okay, yeah, so that would be a good point. But our observation is that often client-side client-side validation is exactly the same or similar to server-side validation. And just to give you some examples here, this comes from a framework called Spring MVC. So where essentially you see the client side on the left-hand side. So yeah, it's some kind of movie application. You need to enter title, release date, the price, and the rating. And all of the expressions, all of the input validations used on the client side that appear, they're essentially reused in an identical way from the server-side code. Okay, so what the framework ensures is that as you write your server-side code, you have all the fields, release date and the title and so on. And already here, so here essentially you have the regular expression. So yeah, so let's see, yeah, like how the genre can look like. You see some restriction on that, what kind of letters you can use in describing that. And that's the regular expression that essentially is reused on the client side because of the framework. Is pushed, exactly in the same way to the client side. Okay, so that's great news for us because that means that by focusing on client side, we have a fairly good idea what the server is doing. Most likely it's doing the same thing. So if you can pass the validation on the client side, then we'll likely pass server-side validation as well. Okay, so that's the important consideration here, that we collect information from the client side to actually learn more about what server is doing. Okay, and here I mentioned, HTML5 is one of the ways in which we collect constraints. You could also have JavaScript that would take an input field and apply some input validation on it, right? So on client side, you can do it in different ways. And yeah, we'll see how we deal with both of these. Questions so far? I mean, yeah, we have a question period, but feel free to interrupt if something is unclear.
One also use error messages that you get out, like they seem to be pretty important. Some of them even mentioned the regular expression against matching.
Well, but the thing is that even without the error messages, you know exactly what regular expression is because it's already in HTML. Yeah. So you don't need to reverse engineer anything here. It's given to you. Yeah.
Provided Spring would have it, I guess the error message is still quite a bit about server side.
Server-side. Yes. Okay. Right. Yeah. If you don't collect it from client side, you could play with the interacting with the server side and getting more information that way. Yes. You could do that. Yeah, potentially. I mean, so there are different things you can do here. You can also maybe from the web page itself and training the right model, you might also be able to derive, okay, what should be the expected input. So yeah, you can play all kinds of games here, definitely. But for us, the beautiful thing that it's already there, it's already in the pattern attributes, so we can use it and focus on regular expressions for which we can design constraint solving techniques. So yeah, but good point. There are other ways of approaching this. Okay, very good. Yeah, I'll talk a bit more about this consistency between servers and client side and how this can lead to vulnerabilities actually. So yeah, we'll come back to that. Okay, so what are we up to? Well, essentially two problems. First one, based on a regular expression that we find, how do you find a string that matches that? Okay, so it's a simple satisfaction problem, right? Okay, this is regular expression. What's the input that will match that? So that's important for the coverage because that way we can increase the coverage by our crawler. However, so another problem of interest, so it's not the same, it's a different one. But another problem of interest here is that, well, if there's a cross-site scripting vulnerability that is present on the web page, then we might be able to find it by injecting in the email field itself. Okay, so that means that what we are also interested in is solutions to the regular expression that contain a payload. Okay, so for our purposes, yeah, let's say it's just script tags to see if they're sanitized or not. So that's a good indication of whether or not there might be a vulnerability. So once again, server sides might be filtering further, but if the client side doesn't do it, so that's an indication of a potential problem that for sure is good to flag. Okay, so these are the two problems that we'll work with in this talk. To solve them, we use SMT solving. And essentially, there's been a lot of things happening on SMT solving front. And recently also kind of particularly constraint solving on strings. And there we are essentially, our starting point is the Ostrich solver designed by Philipp Ruemmer's group, which we are developing to take care of regular expressions in the style of ECMA, so JavaScript style expressions, so that we can essentially have this very nice pipeline, starting with those practical regular expressions, doing transformations to convert them into digestible form that can be used in SMT solving. So a key concept here, and this is a long pipeline, but when it becomes interesting is that when we use automata that can move both ways. So this is automatas as kind of two-way alternating automatas that can consume strings in both ways, forward and backward, and that's needed to match what happens in the regular expressions. And it's alternating in the sense that you use both existential and universal quantification. Existential meaning that you take one of the paths to match an expression, and universal means that you need to apply all constraints, which sometimes you need to do, like in the example I showed, where there are multiple constraints with positive and negative localheads. So essentially, it becomes boosted automata that we need to work with, and by a series of translation, we kind of massage them into non-deterministic finite automata, which can in turn be used in a classical kind of SMT solving. Okay, how we integrate SMT solver in our crawler. So the basic picture is looks like this. Essentially, we call SMT solver on demand. If you go into a bit more detail, essentially, we start by browser looking for a page and identifying an input validation pattern. Okay, so in this case, we found a pattern here in the page. We extract it and we send it to the crawler. So the crawler tries to make sense out of the input validation. If it's just a pattern, okay, that's great. There's something I can send it to the SMT solver right away, but it could be some JavaScript, it could be HTML5 restrictions on minimum or maximum on data. So we essentially combine constraints that arise from here And then after we kind of filter them, we present it to the witness controller, which sends it for, right. So witness controller either sends the regular expression right away into the SMT solver, or if you're interested in looking for attacks, it asks, to kind of generate payload. Okay, which payload would you like to have as part of the string? Okay, so, and then, together, this is sent to the SMT solver, and then the SMT solver gives a solution. So if you're interested in the payload that matches that expression here of an email, then what we'll return here is the string that contains, script and the email address that will be used here. Okay, which the crawler then sends back to the web page and provides it for further interaction. Okay, so yeah, essentially the basic idea here is that the crawler would call the SMT solver on demand whenever encountering some input validation and needing to resolve the constraint. That's the general picture. Yeah, we happen to have excellent crawler and excellent SMT solver in place. Yes.
Do you have some automatic way to generate those payloads, or is like some usual common ways?
Yeah, good question. So in some sense, it's a completely separate area, right? Okay, what's the right payload for each context, right? So what we can do in this part of the picture, it's we have a lot of choices. Okay, because here we focus primarily on the crawling part, we say that we are orthogonal in that. So essentially, there's a library of generic payloads we would use, and for us, we just use script tags just for basic injection. But yeah, you're right. In principle, you can combine this with other types of payloads that you would look for. Yes. Yeah. So in that sense, we are kind of generic, right? So this is generic, and then we happen to use Black Widow for the crawling part and Ostrich for the SMT part. So we need to develop both of them, but together they can implement this kind of on-demand SMT solving for input constraints. Okay, so very good. So with this in place, okay, what kind of input validation can we capture? So the easiest, in some sense, is regular expressions when they're readily available. So we can extract them from HTML5 patterns. However, in HTML5 patterns, we have much more than that. So not just the pattern, but also other kind of constraints. And essentially, we can deal with all of them. So, for example, if a minimum, if there's a minimum in the range, well, we can just pick that value, right? So they're all this from the type of constraints you can have in HTML5. We can essentially express them in terms of regular expressions and include them into the pattern that we need to match. Okay, turns out that so some pages use that, other pages use JavaScript for validation. So maybe developers don't know that HTML5 patterns exist, or it's more convenient to do it in JavaScript. That's something we can also handle. Essentially, we look for the use of method test whenever you have regular expression, and you test it against the input. Our crawler is able to find that and essentially override with the proxy and extract the regular expression and use it for, in the SMT solver. Okay, so that's good. So this two ways we can handle, in our setting. Okay, so so far so good. So this is the start of the journey that I was talking about. Okay, with this machinery, okay, what can we find on the web? What kind of regular expressions are used? Are they vulnerable or not? What do developers typically use? So that's the crawling experiment that we perform. So we're looking at Common Crawl Archive, which is one of the largest archives for the internet. It's very convenient because for like large scale crawling, from where we extract 8,820 patterns. So for our tests, we wouldn't want to kind of unleash our scanner on live web pages because of potentially damaging interaction. So to check how the scanner would do on these patterns, we create our own test bed. where essentially it's a web page per pattern that we extract just to see, how scanners can do to pass it or not. So that's one experiment, kind of large scale. And then the second experiment is, okay, what about open source applications where input validation is used? Can we look at coverage? Because that's one of our main goals, to increase the coverage. In an open source application, we can measure the coverage and see, if our scanning technique would make any difference. Yeah, and for that we look on GitHub by kind of searching. We refine 3 particularly interesting applications that use both client-side and server-side validation, and we analyze them. Okay, so that's the setup here. Okay, so for the first experiment, we look at, remember, almost 9,000 patterns. Turns out that we cover most of them, so vast majority. If you compare it with other scanners, they're lagging behind. What are the typical patterns that only we can solve and not anybody else? So yeah, that's exactly those that I was showing you before. When you have interesting features in the regular expressions, like this one. This clearly looks like a possible kind of password regular expression where you require digits and characters. So no scanner is able to find that one. Yeah, but also even much, what is much simpler, right? So okay, this is the expression for 16 digits. So yeah, for our scanner, okay, that's like super easy to find a solution. That's an easy regular expression. But for the other scanners, since they don't analyze the input validation constraints, I mean, they have no idea. So they try to fuzz, they try to use a library of predefined inputs, and they fail to provide one that is 16 character long. Okay, yeah, so this if you patterns of that nature that show up that nobody can solve, only Black Ostrich. Okay, so more of those, some ranges. Yeah, I mean, you often use various ranges of numerical or different characters or specific phone numbers that are used on web pages. Again, Black Ostrich is the only one that is able to provide input to that. Okay, if you look by domain, so you could ask that, well, there's so many patterns, maybe they're used on some obscure pages, why there are only 8,000 of them from, millions of pages you collected? Well, the reason is that many of the patterns are used on many domains, right? So a lot of patterns are reused all over the internet. So therefore, we also looked at coverage by domain. So essentially, we look at an internet domain and see, okay, can Black Ostrich solve all patterns on that domain, in our data set compared to others? So yeah, here we have 66,000 domains that use patterns on client side. And there again, so the vast majority of patterns solved by Black Ostrich, and the other ones are lagging behind. So interestingly, it's interesting to look at, to compare across different tools. So by head-to-head comparison. So in this matrix, essentially, if you look at the column, it's and the row of a given cell. So the cell tells you how many patterns the scanner in the row can solve that the scanner in the column cannot. So the kind of the head-to-head comparison. So yeah, the impressive line is the green one of Black Ostrich that solves more than the others. And then also interesting to look at the column of Black Ostrich. There are some patterns that we cannot solve, not many of them. Okay, what's the explanation for that? And it turns out that there are a few corner cases. For example, the delete character, which our scanner has a hard time to type in the application, which are used in regular expressions that somehow others are able to pick up. So it's not the kind of fundamental issue, but that's why you see that there are some numbers here, right? That others can solve, but we cannot. So that's the reason for those. So that's the coverage. That's awesome. How about vulnerabilities? So now we're interested in strings with payload that pass input validation checks. So it turns out that we can for vulnerability detection. Also, we detect the most compared to everybody else. So we find the most vulnerabilities. in the patterns, and essentially the gap here is maybe not as big as for coverage, and the reason is that some of the other scanners, they have a more lenient approach as to what actually is a good payload. So essentially, in enemy of the state, you see that okay, this is just a bunch of dangerous characters used as a payload, and it's not the fact that you can. It's hard to exploit that by itself. It just tells you how you deal with dangerous characters. So that way, they get a lot of indications of vulnerability, which might be actually false positive, depending on the expression. Okay, so but nevertheless, we are definitely solving finding most vulnerabilities. So again, if you look at patterns that only Black Ostrich finds problems in, so that will be email, expression that has so essentially anything followed by France. Okay, so as a regular expression, it's super easy to solve. Again, for a state-of-the-art scanner, hard to kind of understand the semantics of that. So this would be typical matches that only we can do when finding vulnerabilities. And in the head-to-head picture, so situation is similar. So again, we're kind of leading by far against the others. And there are a few corner cases related to special characters that like delete that I mentioned before. Okay, so this gives us, this boosts the ability to solve input validations, which is great. Okay, how about open source applications? So if we try this technique on an application we can control, that's great because then we can actually measure the code coverage. So first application is called Alex, and it's for automata learning. When you create a new project, you provide URL, and the URL is matched against a certain regular expression. It looks like URL, right? So for Black Ostrich, this is super trivial to solve, right? And for essentially the other ones get stuck here already, right? They're unable to provide the right URL here. Okay, so so essentially, if we measure the URL paths, we have 25, Black Widow only 9, and the other ones, only get to the login page only. The next one is called Helping Hands. There, it's a phone number that we need to provide to register. So essentially, only one other scanner solves user registration. Everybody else gets stuck. So since we can register, we can cover much more. So this is exactly the cases that I was talking about, that scanning is completely useless if you don't pass the very first registration check. So that's something that we can do. Okay, so a bit more interesting regular expression. Okay, so what is this about? Well, it's it's a typical kind of match you would want to do for DNS records. Okay, and that's the pattern that is applied in the Opera DNS UI, our next open source application. Okay, so then so clearly with this, all other scanners are stuck because only we can solve the expression. Okay, so what about so we looked at different applications, open source or from Internet Archives. Okay, so far we only looked at those that use regular expression patterns, but I mentioned sometimes JavaScript is used. So in the next experiment, we look at most popular web pages and look at 100 most popular ones that actually use some form of input validation. Okay, so it turns out that in the pages we look at, most of the validation are in fact done by JavaScript. Okay, so 56 cases of test and 1 is match, and the pattern is used on 3 websites of those. Okay, so and all of those we can handle, right? From test we can extract the regular expression, which we use in the SMT solver. So it turns out that 86 cases out of 100 we can support and pass the checks. The ones that we cannot handle is the ones where input validation is split into different functions of JavaScript. So we don't run any symbolic execution or don't make any attempts to do any interesting analysis to combine the constraints. But that could be interesting future work to do that. So, but yeah, these are the challenges that we would need to resolve to capture more input validation. Okay, so yeah, interesting problems there. Okay, so yeah, maybe a brief demo. So this is how it looks like if you have a web application and you would want to run our tool. So essentially, yeah, what we'll see is a kind of log of interaction of the crawler and SMT solver. Okay, so this is the page, and yeah, the crawler tries to come up with a lot of input, you know, like trying to get input. And on the right-hand side, you see that see the constraints that pop up that it tries to solve. So let's see. Yeah, so here, for example, we have a regular expression that pops up that is in the phone number field. So being able to solve those, yeah, we advance further in the application. First, we do the modeling of the navigation graph. Then we plant injections and then look for, you know, where this injections would pop up. So it's kind of first part is scrolling, second part is attacking to look for cross-site scripting. So yeah, once we are able to create users, we can explore more of the application and do those kind of injections. Okay, so yeah, so here's an example of a name, regular expression, which our solver returns solution for, right? So, and that's used in the form. Okay, so yeah, that's how the general part works. As we were doing this, we ran into an interesting class of patterns related to emails. And so in the rest of the talk, I'll talk more about that because we found it quite fascinating what kind of email validation is used on the web. Okay, first of all, it's a real problem. There's a hacker community is receiving lots of bounties for email-related bounties. And this is one example. This is Inti. So yeah, hacker called Inti is hacking very successfully on this. And you know, one thing to point out here is okay, 75K in bounties in email-related vulnerabilities. Okay, so this is a real problem. He talks about hacking Gmail, you know, and the validation on Gmail. So yeah, this is a problem in the wild. Okay, so yeah, let's focus on this problem. It's indeed quite fascinating. So by now, we know, is this a secure pattern for email or not? No, very good. So indeed, this is way too liberal, right? We just say that anything followed by @ and so on. So what is then a good pattern? So, well, yeah, so this is easy to inject malicious things. Oh yeah. Let me do a small demo. Okay, yeah. So you're seeing things. Okay, this is way too relaxed, right? For input validation. Why would you want to use it? Well, it turns out that many of the patterns we find on the web are this form. So you know, let me show you a quick demo, illustrate these kind of problems. So I trust this audience not to do any further exploitations. This is just for pedagogical purposes. Okay, so this is a web page that is from our data set where we uncover some of the patterns. So it's a typical form where you need to, you have press question, you need to sign up, and one of the things you specify is email. Okay, so let's look at this source and explicitly look for pattern. Okay, so there you have the input field in HTML, and type text, ID, email, and the pattern itself is indeed of the type that I was talking about, right? So it's anything at anything dot anything. Okay, so if an attacker would try to kind of enter something here, right, and submit, so the browser would say that the browser applies input validation. So the first field is accepted by the browser. Now I need to, what did it say? Yeah, now I need to select item in the list. So I continue providing input here. So far, so good. Now the next one is please provide the email. Okay, so I could provide email of this type. It would be accepted. I could also provide email of this type. with the script, it's accepted as well, right? So it tells me, yeah, when I do this, it says, please select item on the list in the further input. So it's happy with the email. Okay, so if I was an attacker, I would have a good start of an attack here, essentially because email is accepted. Okay, so it is a real problem. On the web, we find many patterns like that. Yeah, I'll come back to exactly how many. So, the question this opens up is that, okay, what is the right input validation for email? And surprisingly, there's no straightforward answer to that, because if you look at standards, there is in fact a standard for email. There's an RFC, it's exactly about that. If you try to read it might take you a weekend to understand what's going on there. So in fact, it's very hard to grasp exactly what's required in that standard. Yeah, I mean, there are reasons for that as well, right? Why there's such a complex standard, but for the web, it's no good because turns out that email like this is considered to be a valid email if you follow the RFC, because of liberal handling of the quotes. So you actually can stick in the payload. It's perfectly accepted. Okay, so that would be really bad email to use, and that's exactly the payloads that we've seen in the attacks that hackers report. So yeah, okay, we cannot use this standard. What should we use? Okay, so yeah, essentially best practice is Masellis approach, and essentially this is the regular expression that is used in the browser when if you use email type in an input form. Okay, then the browser would follow this. Okay, so it's kind of does some kind of sanitization. So yeah, it's a bit more complex, but actually quite reasonable. So if you see, in the diagram here, so essentially it does the allow listing of characters and prevents things like angle brackets, all this malicious things that you don't want to have in an email address. Okay, so yeah, that's what actually browsers enforce. Well, if that's a solution that is known, why everybody's not using that? That's the surprising thing, and that's part of this journey that we ended up doing when looking at email addresses on the web. Turns out there's a huge variety of email patterns, and yeah, they're very different from this one, right? So this is not used so much. People have their own implementations. Just one example here. So yeah, so there's some constraints. Okay, first part should be 64 characters, and then other constraints. Hard to see, yeah, the intuition, but that's one of the expressions we found. And there are many more. Okay, so focusing on this data set. So remember, we found almost 9,000 patterns. How many of them correspond to email? Okay, so yeah, by doing search, we identify 825 patterns that model email. Okay, that's an interesting set. Now, yeah, let's ask a couple of questions about those patterns. The first one would be quite basic. Essentially, how many of them would accept XSS payload? Okay, and since they do, clearly, they would be outside of the MDN. So this is kind of simple Venn diagram. MDN expressions, they don't allow XSS payloads, the sanitizing. Okay, how about, so how many of the expressions from the data set actually accept script tags? Yeah, and this would be an example, right? Like we've seen on the web page, that was problematic. So it turns out 26%. So 26% of 825 regular expressions allow XSS payloads. Okay, so that's quite a lot. Yes.
How many are true positives? But thinking if I would be web developer,
yes,
I would try to keep the RegEx as simple as possible. I would
yes.
call it a filter on the server that just matches any cross-site script tag also.
Yeah. Okay. So yeah, there are a couple of parts of your question. There are two parts of in your question. So one is the matching we talked a bit about client side and server side. So generally, developers try to mirror what you do on server side or the client side. So for many reasons, I mean, you don't want to get unnecessary input to deal with, And then since you already have an irregular expression, it's easy just to dump it on the client side as well. So of course, there's no guarantee that it's exactly the same. And because of that, we cannot claim that those are actually vulnerable. But this gives a fairly good indication that there might be a problem, right? So this is just indication of vulnerability. To test it on the website, for ethical reasons, yeah, we didn't do that. We didn't do, verification on live pages because they would potentially, end up damaging those pages. But for sure, we reported the vulnerable patterns, and yeah, in several cases, developers updated the validation expressions. Yeah, but good point. There's no claim of real problem, but there's a very kind of indicative findings about what might be on the server side.
Is there an equivalent, a server side equivalent of this MDN? This MDN is the browser. What do people do?
Yeah. So, well, so the MDN expression can be used just as fine on both server side and client side. There's like small detail I will discuss later, how they should match. But in principle, I mean, this is what defines what sanitized email should be. So in fact, I mean, what you have here, all of this is exactly to protect server side. On client side, you don't care, right? What email, what user might be entering. You don't care because it's the server that decides whether to use it further or not. So therefore, yeah, MDN comes up with this, and there are all reasons to use it on server side. Nothing else. So yeah, I mean, there's no magic indifference. Yeah. Yes. Yes. Behind the scenes. Yes. Yeah. Yeah. Exactly. Yeah, and that's dangerous, right? So that's where developers can indeed make mistakes. Yeah. Indeed. So yeah, I mean, another paper can be written about server side, but for that it's a different story, right? You need to do different type of experiments, look at frameworks, look at open source projects, and see what's going on there. But for sure, yeah. Okay, yeah. So yeah, but still, it's kind of revealing that not much sanitization takes place on client side. Another interesting question is kind of the other way around. How many of the validation expressions actually are stricter than MDN? Okay, so are there reasons to be stricter? And turns out that yes, in many cases, actually you end up using stricter patterns. And that kind of makes sense. Well, maybe not always. Here you still accept cross-site scripting. You're both, yeah, you're stricter in some cases, weaker in other cases. But here, for example, is an expression that prevents free registering with one of the free addresses, like from a bunch of vendors. So in some applications makes sense, yeah, to be more restrictive than just any email address. Yeah, there's some requirements, and then you can have it on top of email, type. You can have also restriction of more.
Just take the request for checking that they are stricter. Did you use automatically? Is there something like
yeah. So I mean, we checked it at using SMT solver. So to do a kind of subset check, is it empty or not? Yeah.
Oh.
So yeah. Mm-hmm. Indeed. Okay, so yeah, now coming back to Catalin's point about the consistency between server and client side. Okay, it turns out that essentially there's this subtle difference between how you use client side and server side regular expressions. Client side, it's always full matching. Okay, so my string has to fully match the regular expression. On server side, it's not the case. If you use a typical server side engine, it would only check for substrings. Okay, to force it to do full matching, you would need to have some special characters and beginning of and end of string. So you need to force and put it in the pattern if you want full matching. Okay, so this not realizing the subtle difference can lead to vulnerabilities, and that's one example. Comes from W3 docs, one of these tutorials. says like, hey, yeah, on the server side, okay, maybe hard to read, but essentially this talks about checking validity of an email on server side. And it's using a regular expression, which talks about, various allow listed symbols, but it's missing to do this, right? To say that, oh, actually, this has to apply to the full thing, okay? And by missing this means that if there's a, perfectly valid email, and before that email comes a script tag, that's still allowed, okay? So essentially, this is insecure because of this subtle difference that, confusing full matching and substring matching. So yeah, in our thought experiment, okay, this is hypothetical but still interesting. Okay, what if we take the client-side expressions we find and reuse them on server side without the the characters for begin and end of string? How many of them would be vulnerable? It turns out that 61% would be vulnerable. Okay, so if all developers following this with those patterns, okay, then we're in trouble because it's vulnerable expression. Okay, so moving on to conclusions. So Black Ostrich applies SMT solving to the problem of input validation. And in cases when all the other crawlers get stuck, so we are able to make progress, find the right input, and cover much more. So we have good results in both coverage and vulnerability detection, which we see both in client side of applications and our own open source experiments. And in the email study, so we realized that interesting findings, lots of wild variety of email regular expressions, even though you might think that for email this is a solved problem with MDN. Turns out that's not the case, and many kind of potential vulnerabilities there. If you interested more, so we just created a fun challenge. So at Chalmers we like CTFs a lot. We use it in for teaching, and one of the most recent kind of challenges we created is essentially you need to pass validation checks. So you have like 10 consecutive challenges where you need to kind of pass the constraint by a string that you manually kind of come up with. Okay, so this is a way to kind of learn about this by manually passing checks. With the idea is that if you compete with Black Ostrich, it will solve all of them, but this is getting a taste of that in a manual way. So I'm very much encouraged to try this out, and thanks very much.